Welcome, everyone. Thank you so much for joining us today. We're going to get going here in about 5 minutes. Just sit tight, and we're going to start at the top of the hour. Thank you so much for your time and attention. Look forward to presenting construction joint sealants today, an AIA presentation from Patrick Rainey. Be about 5 minutes. So hello, good morning, everyone. Thank you so much for joining us today. My name is Isaac Sorensen. I'm the National Architectural Sales Manager with W.R. Meadows based in the Northeastern U.S. and the New York metro area. Thanks for joining us today for our monthly public AIA series presentation on construction joint sealants. Our presenter today is Mr. Patrick Rainey. Patrick is our Northern California Pacific Northwest dedicated architectural rep based in the Bay Area of Northern California and servicing a large Northwestern territory for W.R. Meadows, including those that I already mentioned. Before I pass the presentation over to Patrick, though, I want to go over a few housekeeping things and also want to put in a plug for our next presentation. As I mentioned, we present on the third Thursday of every month. The next presentation next month will be on selecting the correct underslab vapor barrier. So just a little housekeeping info before we get started. Everyone will be muted for the duration of the presentation. If you have questions, please type them into the Q&A box and double check that you're addressing your questions to quote all panelists. We'll be monitoring the Q&A and we'll be attempting to answer your questions in real time. However, if your questions require a lengthier answer or explanation is a bit more complex, we may hold onto them until the end of the presentation to answer verbally, or if we need extra time to put an answer together, we'll be happy to email you later. So joining me on our panel today is Mr. David Lovelace, our Texas-based Southwest Regional Sales Manager, who has spent many years perfecting and honing the skills in the area of construction joint sealants. And as our Dallas-Fort Worth plant is one of the plants that produces some of the many construction joint sealants that we offer and are discussing today, David is uniquely suited to assist you in answering any questions you might have after the presentation conclusion, as well as our presenter. So this is an AIA accredited presentation. Everyone will be receiving certificates sent to the email address you provided to us at registration. If you included your AIA number, we will also be submitting these credits directly to the AIA. And lastly, on the screen, you'll see an email address, info@wrmeadows.com. If you would like a copy of the presentation or would like to get in touch with your local rep or have additional questions for us in the future, please shoot us an email to info@wrmeadows.com and we'll certainly get you whatever you need. At this point, I'm happy to introduce and to turn over the presentation to Mr. Patrick Rainey.
Thank you, Isaac. As you said, well, so far, I hope everyone's having a great day, and thanks for joining us. As Isaac said, I'm Patrick Rainey, and I do take care of Northern California and Northern Nevada, and also the Pacific Northwest as architectural specialist for WR Meadows. And, you know, we really hope that the information we're sharing today will be helpful to all of you. We've got a lot of ground to cover, so we're going to go ahead and move forward if my slides work. Uh-oh. They worked earlier. Hang on. There we go. Okay, sorry about that. Today we're going to be talking about cold applied construction joint sealants, which play a critical part in our building envelope performance. And this presentation is really intended to explain the basics of joint sealants and introduce the options that are available. The intent being to help specifiers and end users choose the correct product for the project. And the subtitle of this program is a critical part of the building envelope. And I think that's an important message in that I think we sometimes forget or maybe overlook how critical joint sealants may be. They provide great protection in addition to our other systems and also help provide structural protection so that the things that we build and construct can perform and reach the life expectancy that they were designed for. So before we get into the presentation, for those of you who maybe haven't attended one of our previous virtual presentations or maybe aren't familiar with us, a few things about WR Meadows. The WR Meadows company started in 1926 in Elgin, Illinois. Our company is family owned and operated to this day. And we are very excited that in just a few years, we will be reaching our 100th anniversary. We're now headquartered in Hampshire, Illinois, and we currently have 12 manufacturing facilities and 4 warehouses strategically located around North America. And that includes Blue Ridge Fiberboard, which is a part of the WR Meadows family and produces various sound dampening products. And just within this year, some more exciting news for us. We have acquired the Gemite company based in Canada, who we have worked with for many years already, which you'll be hearing more about in the very near future. And then the opening of our new innovation center in Hampshire at our corporate facility, which is going to give us an even greater ability to work on product development and other things as well. So here's a map of our various locations that we have in place to serve you in the US and Canada. I happen to be based at our plant facility in Benicia, California, in Northern California, but I want to also mention that our products are available worldwide. So wherever you may have a project, we can certainly be of help. We started with one product back in 1926, which was asphalt expansion joint. And we now offer over 300 products to help protect your design structures. From our Division 3 offerings, that include expansion joint materials to structural and surface concrete repair materials, epoxies and grouts, to our liquids line that includes curing compounds, curing and sealing compounds and sealers for decorative concrete, and of course the joint sealant materials that we'll be talking about today. And then our Division 7 products, starting with underslab vapor retarders to air, water, and vapor barriers for above grade applications, to our below grade waterproofing systems. And as I mentioned before, we also have our soundproofing and insulation board products from Blue Ridge. And lastly, a quick shout out to another division of WR Meadows, which is our DecoSeal line of products that were developed for the pool industry. And while most people, I think, immediately think of backyard residential pools, these products are used in a large number of commercial type pools as well. So as you can see, we really have a full line of products to help in protecting the building envelope. So again, as Isaac mentioned, just a quick reminder, this is an accredited AIA presentation, and all registered architects are able to collect a learning point for it. So again, please be sure we get your information, including your name, email address, and that all-important AIA number, so that we can make sure you receive credit for the session today. So to take a look at our learning objectives, we will be looking at terminology, sealant purpose and applications, common problems that can occur, also joint design, as well as some of the factors involved that will lead us to successful installations, and also material selection. So as we proceed through the presentation, we will take a look, we'll try to take a look at each of these components. So history of joint sealants. Just to take a quick look at the history of joint sealants, they were first used in prehistory, and people used whatever was available, materials like mud, grass, and reeds. The next step forward introduced other materials such as pine and birch pitch, bitumen, wax, tar, etc., and a few other interesting items there. And then a further progression in the 17th century when an early form of caulk was used to seal window glass. And by the 1920s, first polymers were developed and used in sealants. So realistically, if we look at the timeline of developments in the 50s, 60s, 70s, and even up into the 90s, some of these technologies are time tested and are still used. And while some are relatively new as well, but when we talk about polyethers, for example, and STPEs that have been developed in more recent years, so a wide variety of products and many different technologies. So we can really see from all this, the technology has changed and advanced over time, and what these advancements mean to the construction industry today. So let's look at the purpose of joint sealants. Why do we need them? Well, they provide that critical line of defense for our structures. And for those of you who have attended previous AIA seminars, such as the various seminars we've been presenting over these past couple of years, regarding building envelope products, you have likely heard the word detailed. As we have pointed out many times, the old saying, the devil is in the detail, right? Or the word continuity. Well, many of these joint sealants provide that additional continuity to help prevent water damage, structural steel damage, reinforcing steel damage that can occur or that can diminish our life cycle rather. And then also to help prevent mold and mildew. If that moisture gets into our structures and causes, this sort of damage, in some cases that can be catastrophic. So these products are used to seal. Give me a second. Sorry, so these products are used to seal penetrations in joints and also to help to prevent water and moisture, as well as snow and ice from getting into our buildings' interior space. And if this occurs, a number of bad things can happen, as you can see here, including what we like to refer to as the M word, meaning mold, which is when the lawyers usually get involved, which of course nobody wants. So the further purpose of these sealant products rather, is to accommodate movement, function as part of an air barrier system as well as a vapor retarding system, and to contribute to acoustical control. So what we are trying to accomplish is to prevent water, air, vapor, and sound infiltration into our building, as well as gas and exhaust infiltration. So I want to take a few minutes to look at some of the common terminology that you're going to hear involving these materials, and give you an idea of what these mean and how this can affect your choices when you're specifying these products. And you can see here what some of these terminology bullet points are. So first, let's look at the important distinctions to be made between a caulk and a sealant. A sealant typically refers to a high-performance compound with better quality ingredients, polyurethanes, silicones, STPEs, polysulfides, a typical service life of 10 to 20 years, great physical attributes, adhesion, flexibility, little shrinkage, excellent weatherability, and UV-resistant characteristics. While a caulk, on the other hand, is really a space filler, any low to intermediate performance compound, typically lower quality with limited service life, usually 2 to 4 years. If you have a small gap between your window molding and your drywall and you want to fill that with something, you don't necessarily need a sealant. It just needs a good filler. And they're designed to be covered to provide the nice aesthetics that we want to see. Then we have modulus. Modulus basically refers to the sealant's ability to absorb joint movement in expansion and contraction. Low modulus sealants are better at maintaining adhesion, very elastic, and can accommodate more movement, and they're generally softer. High modulus sealants at the other end of the scale have more limited movement capabilities, so they're well suited for static joints and glazing. But where we really live and breathe more often than not is right there in the middle. Most of our construction joint sealants exhibit a balance of adhesion, expansion, and strength, and are used for most of the applications that we're going to encounter. So we really deal with medium modulus products most of the time. But no matter what sealant you choose for your project, keep in mind that no matter how good the sealant is, it cannot overcome poor joint design or poor preparation or installation. Shore hardness is the ability of a sealant to resist penetration by a pointed object like the heel of a shoe. Typically, low modulus sealants have lower hardness, and conversely, high mod sealants have higher hardness. This is not always the case. Now, ASTM C661 is the standard test method for indentation hardness of elastomeric type sealants, and it's important to be aware that there are two readily accepted scales of shore. There's a shore A scale and a shore D scale. So you want to make sure that you're on the right scale when you are choosing the hardness rating of your product, because the shore D generally represents the harder products, and a shore D of 60 and a shore A of 60 are not the same thing. So make sure when you're looking at these scales that you're on the right scale. Movement capacity is one of the most critical features, right? The ability to expand and contract with the movement of the joint. We want to make sure we know that our joint sealant matches the movement capacity of the joint that it's going to fill. ASTM C719 is the test method that addresses that movement capability and breaks down the 5 classes of movement. And these are plus or minus. So remember that we are not looking at a plus 25, we are looking at a movement of 25%. But from 12.5 up to a scale of 100 with a 50% recovery, which is what that dual number represents, there are different classes of movement. Again, we live in the middle. So the majority of sealants used in construction fall into either the plus or minus 25% or plus or minus 35%. The standard specification for elastomeric joint sealants, ASTM C920, has several test methods within it. So you need to understand that you can't just specify 1 or 2 of these. You want to look at the overall picture. But they include movement capability, hardness, which we've already talked about, tack-free time, and then adhesion. I want to take just a second to talk about tack-free time, because most of the sealants that are installed are single component and are climate dependent in terms of how fast they cure. So while there's a standard with ASTM C679 for tack-free time, the weather at your job site may influence the tack-free time and the cure time of your sealants. Some are dependent on humidity. Sometimes temperature makes a difference. Sometimes it's both. So you have to understand that what you see on the test specification, you may not necessarily get on your job site. So the testing standard for C920-19 or -18 rather. Here are the different parts and pieces involved. This slide indicates the types, grades, and classes of joint sealants. Type S, what does that mean? Well, it means we are designating the type of sealant, a single component for type S, or if it's type M, that means it's a multi-component. So it could be a two-part, which most of the multis are, or it could be a three-part. But either way, it's a multi-component. Grade. So in this case, grade NS means non-sag, typically used in vertical applications, or grade P meaning the product is pourable or self-leveling, used for horizontal or flat applications. And the difference between these two grades would seem to be pretty self-explanatory, right? Well, let me share a little story with you. I got a call many years ago from a city in the state of Nevada that shall remain nameless, and they had a crew out applying one of our joint sealant products to a large plaza area, horizontal application, of course. And they called to complain about how long it was taking and that they were having a hard time getting the material out of the tubes. Well, I was pretty sure at that point I already knew what was wrong. So once I confirmed the name of the product they were using, I had to tell them that they were using a non-sag when they should have had their crew using our pourable product. And after that, of course, they said everything went fine once they got the correct product on the job site. And then we have class, which describes movement. In this case, indicating a movement capability of 35%. It could be 50, whatever that number is, it tells you what the movement capabilities of the sealant must be. Use. T1, T2, and NT refer to traffic grades. NT designates non-traffic. T1 and T2 are two different movement levels in the traffic grade materials. And then the use situation. So the bullet point here starts with OMG, right? What does this all mean? So they refer to substrates that these materials have been tested for. A is aluminum, G is glass, M is mortar, and O stands for other materials. So if you're going to specify a sealant, be sure to pick one that meets your needs. So we look at a spec, ASTMC 920-18, type S, grade NS, class 35, use NTA and O. This would designate a single component, non-sag, 35% movement sealant for non-traffic use that has been tested for adhesion to aluminum, but not glass or mortar. So this might be a sealant to use for glazing around aluminum fenestrations. So you know you're going to have good adhesion to those, but you're not going to glaze with it because it has not been tested for glass. So understand that when you're comparing products, this is your way to make sure you're getting the appropriate product. If, for example, you're looking at something that has, say, a class 25, but your spec is the one we are looking at in the example here, then it doesn't really meet the movement that's anticipated with your joint. So just make sure all the criteria are met when you're trying, that all your criteria meet what you're trying to accomplish. We're going to take a look at just a couple of other terms that you're going to hear throughout this presentation. Joint interface. That's the sides of the joint where the sealant is adhered. And if you look at our illustration here, you'll see what we like to call the perfect joint. Sidewall adhesion on both sides, but the sealant will not stick to the round backer rod at the bottom of the joint. That's just about perfect. And we will talk about backer rod more in depth a little later in the presentation. But again, you'll see on the sides, that's where the adhesion needs to take place. The same with the photo we have here. And that interface is important because we want that sealant to adhere properly. So there's also the consideration of three-sided adhesion. It sounds simple to say, well, if we look at the photo on the right, I'm going to fill the joint and my sealant is going to adhere to all three sides of those points of contact, and it's going to be tightly sealed and never have any leaks. The problem with that is we don't want three-sided adhesion. We want the bottom to be free so that when the substrate, in this case, those two pieces of concrete, expand and contract, the sealant can expand and contract as well. And if the sealant adheres at the bottom, and in this case, we see an example of bond breaker tape, it's that black tape at the bottom there, which in this example will keep this from happening. But if we do have a situation where we get that three-sided adhesion, again, meaning that the sealant is sticking to both sides of the joint as well as the bottom, then this will adversely affect the ability of the sealant to move. So where do we use these products? Well, we could probably just say everywhere and call it good, right? Joint sealants are used in all types of construction and all types of locations, infrastructure, airport runways, highways. These are critical. You can't pour a long, expansive concrete on a highway and expect it to stand up without putting expansion joints in it. bridges, sidewalks, obviously in commercial buildings. And I've already mentioned being able to seal around penetrations and fenestrations in our building envelopes, expansion joints in our walls, in our building structures, our parking structures, plaza decks. The applications are really endless. They're used in all sorts of colleges, schools, prisons. Now something a little bit different, wastewater and water treatment, where our sealant might be subjected to a submersible application. And there might be a need for a special sealant for that sort of application. So you want to make sure you're using a product that is rated to be in the water, or maybe it's a potable water situation. So a water treatment plant where we've got potable water, and you might want to make sure that the sealant has that NSF 61 or whatever you might need in order to use it with potable water. And obviously, huge and tilt-up construction, right, where we're creating concrete panels on the ground and lifting them up into place and then sealing the joints. And also the major retailing chains and big box stores. And then there's the warehouse chains and data centers. These are huge projects, right? And it's not uncommon anymore to see 1 million square foot plus with many of these. So how many expansion joints go into 1 million square feet of concrete slab? The short answer is a lot. So that's a whole lot of joint sealant being applied. What are the substrates? Again, basically everything. Concrete, brick, block, plywood, stucco, EIFS, changes in plane. Maybe it's concrete to aluminum. Maybe it's wood to concrete or wood to aluminum. All of those different substrates. Joint sealants are used, so you want to make sure that you're choosing products that work with your substrate. And then, of course, the building envelope systems where they are used to seal penetrations and seal off fenestrations, and all those places where we want to maintain continuity of our building envelope systems. We have some shots here of these applications, changes of material, brick to aluminum or maybe aluminum to stucco, changes in movement in these products as they expand and contract differently. The sealants serve as that bridge to allow for those products to move independently without losing our watertight and airtight capability. Here's another example. In this case, where the joint is sealed on the interior corner there, so it doesn't necessarily have to be different materials. And then the photo on the right. Keep this one in mind as we move along here. It's regular expansion in a concrete slab, but notice the positioning of the nozzle and the sealant going in. And we'll talk about this a little more later on in the presentation. Also, precast concrete applications. On the left, we have a tunnel being built with precast panels, and the joints are being filled with backer rod before the joint sealant is installed. And on the right, a photo of concrete joints, a sidewalk to a building. That joint needs to be protected. We want to make sure that the sealant doesn't fail and allow water to get down between those areas. There's a little cut joint in the sidewalk there, which isn't truly an expansion joint, but there could also be an expansion joint there in the sidewalk somewhere that is also sealed. And then I mentioned plaza decks and sidewalks. Joint sealants are commonly used in these applications. And then here's swimming pools. First, we have a pool deck application. We can see sealant, there's sealant applied around the deck above the water line, which is a pretty typical residential pool application. And further to that, maybe not in your typical residential pool application, but your commercial pools that often have an expansion joint at the bottom of the pool. There are specialty products and sealants that are designed for those applications. If you're doing that sort of work, you want to make sure that you're using the correct installation methods and the correct sealants. So before we get into choosing our sealants, let's talk about some of the issues that we need to be aware of and things that happen that create problems. And the most common of these are adhesion failure, cohesion failure, and structural failure. And so let's take a look at these one by one. So adhesion failure. When the sealant debonds from the sidewalls, causes and remedies. Well, causes can be inadequate surface prep. And that's true of anything. When we're trying to apply a material that we want to adhere, whether that be paint or a construction adhesive or something like a wallpaper adhesive. Without good surface prep, we're not going to get good success. Surface preparation is at least half the battle. Contamination. Is it clean? Is it free from anything that might adversely affect our sealant? Improper installation. Is the product being installed correctly? And possibly in some situations, improper priming, right? So how do we address these issues? Well, grinding, sandblasting, saw cutting, all sorts of ways to create a good sound surface, and then cleaning that surface, maybe with a power wash and then an air blast to clean out that joint. Proper tooling, making sure that we get that good joint interface so that our sealant adheres well to the sides of our joint, to the substrate. And proper priming. And we'll talk about that a little bit more, but primers can be finicky, and we want to make sure that we're using them properly and applying them properly to get the results that we want from them. Cohesive failure, different than adhesive failure, is when the actual bead of sealant itself fails and tears down the middle. And looking at the photo here, you can actually see a couple of different circumstances. First, the wider joint on the right side, we see cohesive failure where the sealant has ripped apart in the middle. And then if we look at the other joint running in the other direction, it looks like it's pulling away from one side. So maybe that's an example of adhesive failure. So what causes this? Well, again, improper joint design. Or we've got a joint that's too wide or too deep that we're trying to fill. Three-sided adhesion. I mentioned this before. We want the sealant to be able to move in and out with the substrate movement. So obviously we want a proper joint design, the right sealant for the right joint, and then to make sure that it's installed properly. Lastly, substrate failure. A little bit different situation where maybe the substrate itself doesn't stand up to the movement. It isn't strong. Maybe the concrete wasn't poured properly, the design was incorrect, or maybe there's been a washout or something that has occurred underneath the slab that's caused the substrate to be damaged on the edges there. So how do we avoid this? What do we need to do in our specifications and our material selections to make sure that we avoid these situations? Well, for one, and we've mentioned this a couple of times, proper joint design, proper substrate preparation, the proper backing materials, and then choosing the material that fits the requirements of the joint. And then requiring a pull test, making sure that the sealant is performing as designed on the job in real life situations. The standard recommended practice for creating the correct joint design. The rule of thumb is joint depth no less than 1/4 inch and no greater than 1/2 inch. If you're going any deeper than that, you might be extending the sealant beyond what it's capable of. With proper joint design, we are looking for a 2-to-1 width to depth ratio up to 1 inch in width. And frankly, that's about the maximum for a normal joint sealant. Most joint sealants will not tolerate wider widths. They just won't perform. So if you do get into wider widths and larger expansion joints, you might want to consider looking at some of the mechanical systems that are out there to seal your joint. So based on all this, if we have the proper 2-to-1 ratio, the depth is never going to be greater than 1/2 inch. And also consider the hourglass shape. If you look at the diagram on the right-hand side, the sealant has been tooled over the backer rod, and you'll see right below the A on the horizontal section that the sealant is concave, which means that it's been tooled in, which presses the sealant down into the joint, flows around the backer rod to give us that hourglass shape, and also improves our interface with the sides of the joint and gives us the maximum adhesive qualities that we're looking for. So that hourglass shape gives us the joint design and configuration that we really want to see. And another thing to consider is the movement and conditions that can occur. And these take a little bit to think about. But a joint sealed at the lowest temperature will always experience compression. Now, I had a little trouble getting my head around this at first, but knowing that, let's just pick 50 degrees. Your substrates have contracted in the cold, and your sealant is wider than it would be if it was very warm. So you fill the joint with your sealant, the temperature warms, and your substrates expand, which compresses. So if the sealant is installed at low temperature, maybe it won't always experience compression, but for the bulk of its life, it is going to experience compression. Conversely, if you seal something at the highest temperature, now your substrate has expanded, your joint has shrunk, maybe not visibly, but it's shrunk a little bit. Your sealant goes in, the temperature starts to drop, and the substrate starts to contract, and now you're always feeling that extension or expansion of that sealant, and that can be detrimental to the sealant. So for this reasons, many joint sealant manufacturers recommend not installing sealants in direct sunlight. There are several reasons for that, but one of them would be that your joint, the substrate, is probably expanded. The joint is probably at its smallest, and you're always going to get that expansion pressure, which is going to affect your adhesion. So this slide explains the strain joint sealants are exposed to in substrate expansion, which occurs in warm weather. We just talked about that, as well as contraction, which occurs in cold weather. So we have a couple of diagrams of that, looking at a situation where we installed on the left in an expansion condition, and the sealant probably at high temperature. If you look at the joint design, the sizes are 1 inch wide by 2 inch deep, which is a very detrimental situation. And then 1 inch by 1 inch, which isn't ideal, but in real life, a lot of sealants are installed at that 1-to-1 ratio. And then the preferred ratio of 2-to-1 on the bottom. And you look at the strain that's placed on the sealant in the correct ratio, 32%. But in the opposite 1-to-2 ratio at the top, 94%. That's over 60% more strain. On the other side, if the joint is contracting, the strain is more than 12 times as much on the improper joint depth example versus the proper depth. Pressing that sealant up and out of the joint subjects it to damage, possibly from vehicles driving over it or foot traffic or anything else. So now we really have an issue of the sealant having a likelihood to fail, because when we open that roadway or surface back up to full service, if the sealant's been damaged, it may not continue to fill that joint. So this is a little review of joint design. The depth must be sufficient to accept the backing materials, and in some cases, an expansion joint might be used with a backer rod. We want to make sure there's enough room to get our sealant properly installed. The joint should be designed within the sealant's movement capability. Yeah, that might be true, but maybe the sealant should be chosen to meet the joint design movement capability. So maybe that should be stated conversely. The number and spacing of joints is critical, and that really falls on the engineer who's designing the system and is placing those expansion joints. We have to be able to get to the joints. They must be accessible, obviously. And then there has to be sufficient bonding surface for the sealant. I know of a situation, to share a quick story, that one of my colleagues here told me about several years ago, where he was called out to a commercial pool application where the sealant had failed. And it turns out that the contractor had set the backer rod too high in the expansion joint, and the sealant only had at best maybe 1/8 of an inch of bonding surface available to adhere to the side joints. So once the contractor cleaned out the joint, reset the backer rod to a proper depth, and reapplied the joint sealant, everything was fine. So again, all of these steps are critical to a good installation. Substrate preparation. If you don't prepare for failure, right? Well, it really can't be stressed enough that proper joint design is critical, but poor preparation is the #1 cause of sealant application failures. As we say here, probably 95% of callbacks would likely be eliminated if joint prep is done correctly the first time. We need a solid, clean, dry surface to bond these sealants, and that can be accomplished in a number of ways. Grind it, saw cut it, or you can use a high pressure wash, as long as you then allow it to dry, or if it's a small area, maybe just wire brush it. And then clean the joint out, blow it out with compressed air, or brush it out. Make sure that you've got a good sound surface. If it's not a porous surface like concrete or brick or block, maybe it's aluminum, for example, then maybe we can just use the 2-rack method that we point out here. Wipe the surface clean and then follow with a dry cloth. We want to make sure that everything is off of the surface before we apply our sealants, so that we're bonding to the proper area and there are no contaminants. Substrate preparation in all things adhesive really is paramount. There are four main benefits to backer rod: to increase elasticity in the joint sealant, to reduce excessive amount of sealant being applied into the joint, which helps to control the sealant cost, to force the sealant into contact with the sides of the joint, which gives us a superior bond by creating that hourglass shape we've been discussing, and to create a bond breaker, which allows the joint to be easily cleaned out and refilled with sealant as needed over time. Closed cell rods are a foam material that has a surface skin. The material will not wick moisture, which makes it suitable for joints with a high presence of water or dampness. They are dense and firm and intended for outdoor and heavy-duty construction. The product will force sealant against the joint sidewalls, again, which provides us maximum sidewall adhesion. Sealants will not adhere to them, which eliminates that risk of three-sided joint adhesion failure. Open cell backer rod, also a foam material, does not have a skin. It can easily compress and return to its original state due to unrestricted air movement. This flexibility makes it easily conform to sealing applications and helps limit the depth of the sealant while also adding good sealant airing, which can reduce drying or setup time. And then bicellular rod also refers to as soft rod. It's basically a hybrid between the open and closed cell rods. It offers high compressibility, but has a closed cell outer skin to resist moisture. It is ideal in irregular joint applications where self-leveling flowable sealants are employed. And these are usually used for applications with high heat, and some of the DOTs use bicellular rods and hot joint sealant applications. Expansion joint materials, which include asphalt expansion joint, which is the first product our company ever produced. Asphalt fiber, foam, sponge, they all react differently to our sealants. And again, the idea of the bond breaker tape or backing tape that prevents that three-sided adhesion. Joint sealants will adhere to asphalt fiber, and that's a bad situation when we get into long-term performance of our joint sealants. If joint sealants become attached to the joint filler so that movement is prohibited, they won't be able to perform their intended function, which is to seal the joint against water and debris entry. So again, this is where bond breaker tape comes into play. Many of you may have heard of a plastic cap product that installs over the asphalt fiber so that we have a pre-measured depth for our sealant, but sealants may stick to that as well. So maybe we have to remember to use our bond breaker tape again to prevent that three-sided adhesion. So why use backer rod? Well, having a properly designed joint with an improperly placed backer rod is just as likely to fail as an improperly designed joint without a backer rod. And to attain proper wetting of the substrate, we want to make sure we have a proper surface and proper depth. Control the sealant depth. Again, remember that our depth should be a 1/2 inch maximum to prevent that three-sided adhesion. Sealants generally do not adhere to backer rods, and make sure that the backer rod is larger than the joint. 25% larger is really the rule of thumb, so that we get a good tight fit, and it just makes sense, right? And this gives us a couple of benefits. If we just lay a backer rod in the joint that's loose and we don't have a good tight fit, the sealant, especially if it's a self-leveling material, might just flow around our backer rod and flow down and pour into the joint, which is not going to provide us a good seal, because now we're controlling the amount of sealant. We're now not controlling the amount of sealant we're using. So we're just pouring our sealant down the drain, so to speak, which is a waste of money. But if that backer rod is placed correctly, it provides us a good area for our tooling base. If it's tightly fitted into the joint, when we press our sealant in to achieve that good interface with the substrate, it will hold its ground not only to our tooling effort, but to traffic, to give us the support that the sealant needs and the adhesion to the interface that we want. Remember, the backer rod is the last line of defense before the sealant is applied. So we've got our joint, we know how to prepare it. So how do we decide what joint sealant to use? And there's plenty of them on the market, and they all have different sorts of applications. So we need to select a material to handle the anticipated joint movement, the right sealant for the right joint. Does it adhere to my substrate? Remember that C920 talks about whether it's glass, aluminum, mortar, different substrates. Does the joint size allow for sufficient placement of the selected materials? Expansion joints and seal joints generally have to be wider than 1/4 inch in order to get the sealant in. and to have it fill and move properly. So just a standard saw cut joint that you see in floors to allow for control joints doesn't really work well with sealants. Will the product perform under stated conditions of use? Does it fit my job? Not every sealant works for every application. Is there a history of application success? Most of the sealants you see today have been around the market for a while, and the technologies are time tested. And does the manufacturer provide third-party testing? Have they gone out to reputable independent testing labs to obtain reports to certify that the sealants comply with that ASTM-C 920 standard that we've already talked so much about? As I mentioned, there's a ton of different sealants out there, so you want to make sure that you're selecting the right one for your project. Latexes and acrylics. Again, we're really looking at materials that should be referred to as a caulk, probably not a sealant. They don't have the physical properties to match up with the urethanes and silicones and STPEs that are on the market. Relatively low movement, 10 to 12.5%, used more as a filler for interior applications around sinks, bathtubs, etc., where the service life isn't as critical and we can easily replace them, and to paint over them to create that nice aesthetic that we want around our interior and exterior areas, so that we're not looking at gaps between moldings or within moldings. We can fill them and paint them, and their cost tends to be in the low to moderate range. Butyls have been around a long time, solvent-based synthetic rubber materials. They have wonderful adhesive properties. They bond to almost anything, including you, if you get them on you. They don't move very well. They generally have limited movement accommodation, less than 10%. They're not as good at weathering as some of the other sealants on the market, but as I said, they do adhere very well, and you'll see them in areas where there's concerns about adhesion of the sealant. But they are hard to work with, they're stringy and hard to tool and want to stick to everything, so it makes them a little more difficult to deal with. And when you're working on the exterior of a building, the last thing you need is to get a bunch of butyl all over the place and have to remove it. Cost of butyl sealants tends really toward the moderate range. Polysulfides, the first high-performance sealant chemistry, has been around for a very long time. Maybe not as good as some of the newer sealants, such as the newer urethanes and silicones out there. They do have excellent adhesion. They don't recover as well as some of the other sealants. And by recovery, we mean that when they expand, they may not contract back as well. They can be formulated for good chemical resistance. They're used a lot in the commercial pool and residential swimming pool industry because they're chlorine resistant, and also good for submerged applications. You want to remember that proper priming is basically always required in those submerged applications. And polysulfide sealants often require a primer in other applications too, and they tend to be relatively expensive. So now we go from the oldest chemistry to maybe the newest chemistry, STPEs, Solil terminated polyethers, and also MS hybrids, modified silicones. These are relative newcomers to the sealant world. STPEs are becoming more and more popular in the market because they bond very well. They have good UV resistance, but they don't really work well with glass, and they can't be used for glazing. But they have good weathering characteristics, not only to UV, but also to the physical elements. Great adhesion, great expansion and contraction. These products are very high solid and very low VOC. And here in California, where I'm located, the VOC capital of the world, that's definitely a very desirable trait. And the other thing that we found is that they work very well in the building envelope systems, the air barrier and air moisture barrier systems, in part because they have good physical properties, but they're also relatively benign, and they're compatible with a wide variety of products. But now that I've said that, don't just go out and pick a polyether or an STPE sealant to go with your weather-resistant barrier system or your air barrier system. Make sure that you consult the manufacturer, because while they are fairly benign and compatible with most building materials, they may not be with yours. So again, remember what we said, do your due diligence and check with the manufacturer first. Polyurethanes, probably the most widely used sealant in the industry for a number of reasons. They're generally economical, but can't be used in structural glass assemblies. They have great physical properties. They are tough, have great expansion, great contraction, good movement capability, class 12.5, 25, and 50. Good UV resistance, excellent weathering. And as the advent of VOC regulations has become more strict, lower VOC formulas are available. They're forgiving, and most of the time when you're walking down the street and you happen to glance down at the sidewalk and the joint is sealed with something, chances are it's a polyurethane. They're also paintable. You should consult your manufacturer on this, but in trying to paint over any of these high performance sealants, it's important to understand that these sealants are designed to move. And if we're going to coat them with something, that coating paint should also be designed to move. So let's think about that for a minute. If I take a sheet of rubber and I paint over it and then I bend it, and if I've just used a regular standard latex paint, that paint is going to crack when that rubber moves. Or if I expand the sheet, that paint's not going to be able to move with that expansion, and eventually the paint's going to come off that sealant. So if you're going to paint over these sealants, make sure that you're getting the right material to coat them. Silicone is not necessarily a newer technology, but a very high performance technology. The silicones adhere to a wide variety of substrates, glass, they're used for glazing and structural glazing, concrete, wood, all sorts of different things. Generally do not require a primer, although in some circumstances a primer could be recommended. Excellent UV resistance and great weathering capabilities. They can have good chemical resistance and temperature resistance, and they're good for sealing the perimeter of fenestrations. Generally not paintable, not much sticks to silicone. They have the highest movement capability, class 50 to 100, generally longer service life and continued flexibility over time. But silicone sealants can have a strong odor and take considerable time to fully cure. In general, cost for the silicone sealants is generally in the high range. So which one should I use? Well, again, as with most building materials and product decisions, the answer is it depends. But the goal is to determine the best sealant for the application and compatibility to the substrate, the budget, service life, etc. So this is a nice quick reference chart that does a good job of showing which sealants might be suited for which applications. If you'd like to take a picture or screenshot of this chart, please feel free, or contact us afterward, and we'll be more than happy to share it with you. Note that we have a rating system at the bottom to help determine suitability, and these sealants are listed in the same order in that we discussed them, from latex across to the higher performance polyurethanes, silicones, and STPEs, which fall mostly into the excellent category, with most of the uses that are listed here. I suggest that you keep this chart close by when you're starting to explore different types of sealants and what your best options are likely to be for different applications. There's a lot of good information here, but remember, this is just a guide and hopefully serves as a good starting point for you. But you might want to talk to your manufacturer's rep and get some help in deciding what might be best for your specific application. So talk to your trusted reps and pick their brains. Installation, another part of our designing for success. This slide illustrates some of the failure possibilities associated with joint design, in many cases being the result of improperly placed or selected backer rod. So let's start with number one on the right-hand side here. We can see that this is an example of proper joint design. Our width to depth ratio is correct, the sealant is tooled properly, and the backer rod has been placed to the proper depth. Exactly what we've been talking about all along, right? Our adhesive and cohesive failures go way down in predictability when the joint design and sealant application is done correctly. The sealant needs to be gunned in at the middle of the joint so that if it's a self-leveling material, the sealant will flow out properly. And if it will need to be tooled, the sealant is evenly gunned in. I showed a photo earlier in the presentation where we saw a nozzle being set in the middle of the joint and the sealant being installed evenly. That's important not only at the width of the joint, but also throughout the entire length of the joint. So in examples 2 and 3 here, these are the things we want to avoid. Example 2 here, we're adding too much depth of sealant in our joint design just by pushing our backer rod in too deep, which means we have lost that proper width to depth ratio we want. So now we have a good chance of adhesive failure, where the sealant wants to pull away from the sidewalls. And looking at example 3, this is kind of the opposite situation of example 2, right? Instead of too much depth of sealant, now we don't have enough. The sealant is just too thin and too shallow across the joint to develop the cohesive strength that we need. And it can end up tearing across the middle of the joint somewhere, as we see here. And that goes back to our discussion of cohesive failure, right? So in this case, that backer rod did not get set deep enough into that joint. And I love this graphic because it shows these examples side by side so that you can actually see the differences between a good, proper application and poor applications. And above that graphic is a shot of someone placing backer rod by hand. But next to that is an example of a tool that can be used for putting that backer rod into the joint and setting it at the correct depth. And there's many versions of these tools on the market, from small handheld to walk behind versions. But mainly, I just wanted to make you all aware that these tools do exist, and experienced qualified sealant applicators are used to using these tools to help them do their job. Priming. The intention of using a primer is to improve the bond of the sealant to the substrate. Priming is almost always required in submerged applications and sometimes in horizontal applications as well. But keep in mind that priming is not a substitute for good prep, okay? The primer can only be as effective as the condition of the substrate allows it to be. In this joint application, you can see that they've placed blue painter's tape on each side of the joint, which can help to keep the primer from contacting the surface above the joint and can serve the same purpose when the sealant itself is later applied. Again, to help set a nice clean line with no overrun out of the joint. Kind of like using painter's tape when you're painting a wall to keep a nice straight line. And if a little gets on the tape, it's okay because you'll be peeling it off later anyway. And for less experienced applicators, this is a good way to learn to apply sealants until you get the hang of it. Kind of like training wheels, so to speak. Also, for proper primer application with a brush like we see here, you want to prime both sides of the joint without getting it outside of the joint and up onto the substrate, which could cause staining, and that can be a real pain to have to clean up. And you want to prime and apply your sealant the same day. Further to this point, always go by the manufacturer's priming instructions, which can vary. Sometimes if you apply the primer and leave it for too long before applying the sealant, it loses its priming ability, and in some cases it can even become a bond breaker if it dries and can actually prevent the sealant from adhering. So if the instructions say all primed surfaces must have material applied within 24 hours, for example, then you either need to adhere to those instructions or reapply the next day before you do apply your sealant. And then an adhesion test. Include a note in your specifications that we want to do a test on the site for adhesion. The field adhesion test is simply a hand pull test of a cut area of joint sealant. We're not going to get into too much detail on how the test is actually performed, but there are YouTube videos of the adhesion test being done that you can take a look at. So if anyone is interested in seeing the actual field test performed, take a look at one of these. And the pull test is a good indicator of the fundamental adhesive properties of a sealant on a particular substrate. So we want to first apply our sealant to the substrate and let it cure, because curing is important so that it's not just dry, but it's been allowed time to develop its full adhesive quality. And then we're going to pull the sealant back. And as the diagram here shows, we are looking for cohesive failure. We want the sealant to rip right down the middle and hopefully leaving the adhesion to the sidewalls intact. So if our application passes this test, we know that the joint was cleaned properly, the backing material was placed properly, and that we're going to have a long service life of that sealant application. Master Format Section 079213, Guide Specification for Elastomeric Joint Sealants. Some sections to consider: 1.03 to reference our ASTM standard 661, different sorts of things. Quality assurance. Does the manufacturer have experience? Does the installer have experience? And make sure you're specifying product sealants and primers that meet local VOC regulations. Materials. This is where our C920 comes into play, right? Do we do a performance specification and you have to meet this alone? You want to make sure you're getting a silicone if you want a silicone, because just C920 may not be enough to indicate that you want a silicone and would otherwise allow for a urethane to be used, for example. Accessories. Do we want a primer? Do we want a backer rod? Let's make sure the accessories that you want are listed. And then the all-important joint preparation, 3.02, that we've been discussing throughout the presentation, right? We want to make sure we define the preparation that's expected. And that might be as simple as saying joints should be prepared as per manufacturer's written instructions. And that's fine, just as long as joint prep has been accounted for and addressed. And again, as we mentioned earlier, 95% of a successful application is having proper joint prep. So we've covered a lot of ground today, right? In summary, we've learned that joint sealants are an important part of the performance and longevity of the building. We've looked at the difference between a sealant and a caulk in terms of performance characteristics. As we discussed earlier, latex and acrylics tend to fall into the caulk category, which are best used on interior applications. And when we get into critical parts of the building, we want to use a sealant. At the job site, slow down the process to make sure that everything we've talked about has been done, from joint sealant design to prep, and finally to installation of the sealant. All of these factors are critical in helping to ensure a successful application. So as we've seen today, there are many different types of joint sealants out there on the market, and we've tried to give you some of the information and tools that you need to decide what is best for your particular project. Again, not everything works for everything. So that concludes the AIA portion of the presentation. Again, thanks to all of you for joining us, and I hope the information we've shared today will be helpful to all of you. If you want more information, there are several ways you can reach us. As Isaac said earlier, info@wrmeadows.com. You can also call us on the 800 number you see listed here, and it will connect you to the closest WR Meadows office to your location. Our website, www.wrmeadows.com. Lots of information here, data sheets, SDS sheets, guide specs, product videos, and we now have an area specifically for architects and engineers to make it even easier for you to find the information you need. And more recently, podcasts and blogs. These are new additions as well, with some great industry information. And my personal favorite, our new chat box feature, which a lot of you have already been using. So we have a lot of great tools available to you, and frankly, our goal is to help make your jobs easier by making it as quick and easy to get the information you need or to get the help you need from us as quickly as possible. And one final thing, and then I'll turn it back over to Isaac. I just wanted to let all of you know that we have recently put together a very comprehensive document that's intended to be a quick reference chart for our Division 7 products. And if any of you would like a copy of this, again, just email us at info@wrmeadows.com, and we'll be happy to get that to you. And with that, thank you all very much. Appreciate your time, and I'm going to turn it back over to Isaac.
Thank you so much, Patrick. That was an excellent presentation. I hope that everybody that participated today enjoyed the presentation and learned something. We have a few minutes to go over some questions if you have them. So again, if you do have questions and you have the time, please throw them into the Q&A and address them to all panelists. I do see a few things in the chat, but first of all, we did receive a couple of questions regarding how to obtain our presentation. And as Patrick mentioned, the simplest way to get a copy of the presentation would be to shoot us an email, info@wrmeadows.com. And also, this presentation will be available on our YouTube channel through our WR Meadows YouTube channel. So I have previously introduced Mr. David Lovelace, works out of our Texas branch as a manager there, and is also an excellent resource for all things joint sealant related. I've asked David to join us here today. So there's a few questions that I'll get into it, but not a lot came through. So I'm going to start with this one, and we'll see if anything else pops up back into the Q&A as I get into this. And then, if this question needs a longer answer, or if those that are participating feel like they would like to email you rather than answer it publicly, we will certainly get back to you. So this first one is, if using the Deco foam with 1/4-inch joints, is polyurethane the best sealant?
when using deco foam, that was the question, Isaac.
Yes. I think that,
Um, I guess and David, you might want to chime in on this too. I guess it depends on the application. In general terms, I would say yes. But if it's say an application around a pool deck, the polysulfide product I think would be a better choice.
agreed.
So I think it kind of depends on the application. I guess in general terms, I would answer it as probably in a standard commercial application. But again, if it's around pool chemicals and a swimming pool type application, that's what we have our polysulfide products for. So I hope that helps answer the question for you.
Patrick, if I may,
Sure.
that seems like a really small question, but I think as I'm sitting here thinking about it, I don't think that it really defines enough perspective of what we're trying to accomplish. Really, any of the joint sealants discussed today are compatible, if you will, to the Decafoam, so that leaves no problem. A 1/4-inch joint, we're not really anticipating a whole lot of movement. So, maybe you don't need a silicone, which can accommodate greater movement. But in general terms, they would all work. I think you just have to identify any other particulars that may be of issue that you're trying to deal with. Maybe you've got something, maybe cleaning solutions or something that's going to go on top. Well, that may lead you to a more chemically compatible type joint sealant, or if you're going to have something around some fuel oils, like you're in a gas fueling station, that may direct you to a more fuel resistant sealant. So, in general terms, I don't think there'd be anything wrong with how the question was phrased using polysulfide or with the Decafoam, but I think you have to further delve in a little bit to come up with an appropriate sealant to be used.
Excellent. Agreed, David. Great answer. And I've got another one for you here that's a lot to unpack, but maybe maybe you could give it a crack. We'll see. Would you suggest polyurethane or silicone for roof flashing?
Ooh, that is a good question.
Yes, it is.
Polyurethanes are used in roofing applications all the time,
Yeah.
whether they're sealing off termination bars or being used in pitch pan. The use of a polyurethane is a liquid flashing. I think that the main limiting factor there is going to be the type of roof membrane that you're applying to. So you have some compatibility concerns there, both from a chemical standpoint and an adhesion standpoint. The second thing is, a polyurethane, while UV stable, the life expectancy of exposed polyurethane is a lot less than that of a silicone. Silicones, you may get up to 20 years. And I don't know about anybody else, but I'm not going to risk a water leak from the roof without fully investigating everything that needs to be investigated. Mm-hmm. Whereas I think that maybe a product was missed, which is the STPEs or polyethers. Those are used in liquid flashing applications a lot in the air barrier world. So I think that actually may be a little bit better direction to look than the polyurethane.
Great answer. Thank you so much, David. And I got another head scratcher here. Please discuss masonry mortar joints that are to be raked, then bond breaker tape and sealant applied to protect the masonry mortar joint. I could read that again. Please discuss masonry mortar joints that are to be raked, then bond breaker tape and sealant applied to protect the masonry mortar joint.
I'm trying to wrap my head around that. So as I'm understanding it, we're gonna build some sort of masonry wall. We're going to strike those joints, and then we're going to put a bond breaker tape over that, and then seal over all of that with a bond breaker. I mean, with a joint sealant. I'm trying to have a picture in my mind when I would do something of the sort, and I'm struggling with it. So I may be misunderstanding the question. I'd be more than happy to talk individually with the question asker, just so I could have a better understanding of what the situation is.
Agreed. We'll be happy to get back to this question asker with some answers. We've got a lot of folks that jumped into the chat, both to ask for the presentation and also to thank Patrick for such a great presentation. Again, the presentation is available. Please shoot us an email, info@wrmeadows.com. And I think we have one more I'm going to get into here, if I can pull it up, from the Q&A. This is a little question that says, the backing has to be installed half of the depth of the backing or of the gap, ? And again, it says the backing, meaning backer rod, has to be installed half of the depth of the backing or of the gap.
So we're talking about width to depth ratio in this question. Ideally, if you have a 1 inch wide joint, you're going to insert the backer rod where the depth, if you took a straight edge over the plane of the joint, and then you measured from the bottom of the straight edge to the top of the backer rod at the center point of the joint, is going to be half of the width. So that would make you have the 2-to-1 width to depth ratio, which is ideal, at least for the sealants that we're talking about today.
Excellent. Thank you. And we have one more. Is there a recommended masonry or brick joint sealant or sealants used for soft joints that are compatible with SBS rubberized asphalt through wall flashing?
Great question. And I wish architects of the world would ask this question more often, because it is a true compatibility issue. Some sealants are compatible from an adhesion standpoint to the carrier films of the through wall flashings or the flashings that are used. Some are not. And then you also have a asphaltic compatible issue, where either the polymers in the rubberized asphalt will attack the sealant, and you can get some cold flow and some discoloration, and maybe even in the heat of the day or in some warmer climates, the sealant will sort of soften enough that it flows out weeps and other ways that it could get out and expose itself. Typically, polyurethanes should not be used in that condition. I do understand there are a few manufacturers that have some polyurethanes that they say are compatible. I look at those and sometimes I wonder whether or not they are or not. But those manufacturers can state what they want to on their data sheet. Silicones, generally not, unless you're using a silicone type weather barrier system, because as Patrick said, silicones really only stick to themselves. So that sort of leads you into the STPE or the polyether arena. Those generally have adequate enough adhesion to the carrier films, and they do provide us a level of chemical compatibility to exposed rubberized asphalt. Now, that's a general statement. I do think it's wise in all cases to go and verify that. And something that I think we're all having to learn to live with in today's world, where building materials are scarce at times and raw materials are scarce. We as a manufacturer are not going to put on a letter or make a blanket statement that X sealant is compatible with X product. Because if we do, we don't know if at some point in the manufacturing process that sealant changed. If we're not manufacturing, if it's manufactured by others. And if they changed the recipe, so to speak, and had to put something else in there that we're unaware of, and there's a letter floating around out there, we've created a pretty possibly big issue for ourselves. So I think you have to take that case by case basis or keep everything within a family of manufacture, which is difficult to do. But I think those are really some cause or some words of caution that I would keep in mind.
An excellent way to approach that that question, which can get a little dicey again if you're one manufacturer to another. Always good practice to reach out to the manufacturer and discuss. There's another question that came in here. What are the options available to prevent adhesion to the backer rod?
Well, I mean, you could use bond breaker tape, but adhesion to the backer rod, since the backer rod is floating, it's not adhered to the sidewall or, something like a rigid expansion joint filler that can expand, move, shift, float, whatnot, really poses no problem. So, while you may get some adhesion to the backer rod, if you do, it's a benign effect.
Great. There's another question here. Can you elaborate on interior floor sealant options, specifically floor movement joints, which I usually specify urethane?
I think you got to take a little bit context here. What is the floor used for? If this is a heavy use warehouse area, you're going to want to deal with something that's probably a little bit harder. It's not to say that you can't get a urethane that is hard enough to absorb the abuse of forklift traffic. Generally, those joints are pretty stable. They're not going to open and close considerably because it's should be a fairly constant inside room temperature. So, I don't think you have to have anything of silicone nature, but the real limiting factor there, I think, is what the floor is used for. If it's foot traffic, I would have no problem with it. Maybe even light vehicular, hand carts and that kind of thing. But if it's a busy industrial setting or distribution center that's got forklift traffic quite often, I think I'd move to other kinds of sealant, either a flexible epoxy or a polyurea.
Excellent. Man, these questions just keep coming in. I'm enjoying that folks have stuck around for the question and answer period. Thank you again, David Lovelace, for joining us.
Thank you.
You can reach David Lovelace at dlovelace, that's with 2 S's, at wrmeadows.com if you have further questions about joint sealants, or of course info@wrmeadows.com. That's dlovelace with 2 S's at wrmeadows.com. This next question: what's the best option to bridge between polyurethane and asphalt-based products? Is there one?
Epoxy.
And there you have it. How about in masonry joints? When do you recommend a joint versus a mortar joint? I'm sorry, a sealant joint versus a mortar joint. Maybe that's
I mean, that's a design decision. The architect or engineer is going to build in some expansion capabilities within their block wall or their brick facade. And obviously, if you've got that designed in, you would not want to put a rigid mortar in there that's, after a period of time, it's going to be very ineffective. And there's probably going to be some openings to allow ingression of things we don't want to get in. So I would go back to the structural side or the design side to determine that.
excellent. And I think the last one here, we've gone 15 minutes over the hour. I'm going to believe this is our last question. A pretty simple one, but always a good one to ask. Is there a simple method of determining types of existing window sealant used from a visual non-invasive review? For example, silicone versus polyurethanes.
Ooh.
Mm.
And Patrick, you may have some thoughts here because I know you've spent about a number of years on job sites, but I can generally identify a silicone from something else just by touch and feel, and that's just through experience. But if I'm trying to determine a polyurethane from a polyether, probably couldn't do it, other than maybe some sort of color, because some polyethers come in some pretty wild color arrays. And the polysulfides would probably have never been used in that type of condition.
Yeah, David, you're right. That's a tough one. Just from a visual, just based on a visual, I think.
Yeah.
I think it might be safe to say as well that silicone tends, I mean, if you're getting a clear sealant, you're looking at a clear sealant, it is likely to be a silicone. But
I would say
again, that's that's a tough call, and time and experience. Of course, you can always take a picture and email us, info@wrmeadows.com. We'll see what we can do. I want to thank our panelists today, Mr. David Lovelace. I want to thank Patrick Rainey for this presentation, for the rest of the panelists joining us today from our architectural team at WR Meadows. Again, for a copy of the presentation, info@wrmeadows.com. And I want to wish you all a wonderful day, and thank you again for joining us. Our next public AIA presentation will be on the third Thursday, as always, of next month, 1 p.m. Eastern, noon Central, and we look forward to having you join us there. The next presentation is on selecting the correct underslab vapor barrier. And again, thank you to our presenter, Mr. Patrick Rainey, for a great presentation, and thank you to all the participants for sticking around and asking such great questions. Again, if we didn't get to you today, we will be emailing you within the next few days to make sure that we answer all of the questions that came in. And again, if you provided us with your AIA number and your email address in registering, we will be submitting these for registration with the AIA. If we missed you or you forgot to add that information, email us, info@wrmeadows.com. Thank you, and this concludes our presentation for today. Have a wonderful day. Take care.
Thank you.